Hi everyone, Steve here. As the title suggests, I'm going to be taking a look into SD cards and in particular how we interface an SD card into a larger system. How do we electrically make all the connections? What got me interested into looking at this was actually a comment on one of my other videos. It was a comment on a video about a temperature sensor, and you can see it here. This is from Saskia H, and it reads, "Hi Steve, could I integrate the sensor into a small device and use it as a temperature data logger? Thank you and best regards, Saskia." Well, thank you, Saskia, for your question. It's a very good question. Unfortunately, the short answer would really be no, because the temperature sensor just literally reads temperature and that's all it does. To get into data logging, we need a little bit more circuitry. And the main thing we need is somewhere to actually store the data, somewhere to log the data to. And I think a good choice for that would be a SD card. So it really got me thinking about, what would be required to build a system like a temperature data logger, and what would we need? So I thought I'm going to start by looking at an SD card, and the other reason why I'm interested in SD cards is because of my Z80 computer project. I might eventually want to incorporate an SD card as a form of removable media. I think that might be a little bit too complex right now, so I'm not going to cover that on the Z80 computer series right now. But I thought I would at least take a look at SD cards and how they work, how we can connect up to them, because that extra knowledge can't hurt. So I'm going to start with trying to connect one up to an Arduino. Now, I know we could just go and buy a module. There's a couple of modules here. This red one here seems to be literally just a breakout board. I think it's just literally breaking out the connections. And then we've got another one here which actually has some additional circuitry which intrigues me, and I want to know, what does that circuitry actually do? Why do we need it? Now, of course, I could just go and buy one of these boards, but I wouldn't learn anything by doing it that way. So I want to look at the actual circuit and see how can we build one of these boards ourselves, or myself, and once I've got that knowledge, I should be able to incorporate that into a larger design. So I thought I would head over to Wikipedia, because there's no doubt going to be a little bit of information there. I mean, maybe this is not the best source of information, but certainly going to be a good starting point. So we can see here on the Wikipedia page, we've got some images of the SD cards. Here is the standard size SD card. Looks like there was at some point a mini version, and then the more familiar micro version. So that's what they physically look like. And if we take a look down here, we've got transfer modes, and we can see that we can actually communicate with this over the SPI interface, and we can operate it in SPI bus mode, or we've also got 1-bit SD bus mode, and we've also got 4-bit SD bus mode. But I'm going to concentrate on the SPI bus because that's something I'm more familiar with. So I haven't read all of this Wikipedia document, but I believe the SD card came from an earlier device called an MMC, which stood for multimedia card, and it looks like it's physically the same size as the standard size SD card. So I guess things just evolved over the years. New and different designs came out. So you can see the original MMC card had 7 pins, and then the SD card added 2 more pins. We've got here pin 8 and over here pin 9. And then it looks like the mini SD card added 2 more, giving us pins 10 and 11. And then it looks like they cut things back a bit with a micro SD and cut back to just 8 pins. I guess they had to compromise on the physical size. So this chart gives us all the pins with their numbers and descriptions of what they do, and we can see we've got the original MMC pins, and then we've got the SD card pins, the mini SD pins, the micro SD pins. And this column tells us the official names, and then we've got the logic and descriptions of what they actually do. Now, an important thing to note is if we look at the pins of the full-size SD card and the micro SD card, we can see that the pin numbers are actually slightly different. So we've got the chip select is pin 1 on a standard SD card, but it's pin 2 on a micro SD card. And data in is pin 2 on a standard SD card, but it's pin 3 on a micro SD card. And then the micro SD card doesn't have this VSS connection here, but there is another VSS connection down on pin 6, which does exist on the micro SD as well as the standard SD, and that's actually the ground. But there onwards, the pin numbers seem to be the same. 4, 5, 6 and 7 all seem to be the same. So it's just those pins 1, 2 and 3 we need to watch out for. So then what I thought I'd do next is take a look at an existing design with a schematic. And Adafruit is always a good source of information because their designs are all open source and they share everything. So it's a great learning resource. So this board here is actually a data logger shield, which is very interesting because that was what the original question was really asking about. But we can see in their design they're using a full-size SD card, so we need to bear that in mind when we're looking at the connections. But we can also see they've got some additional circuitry here. There's a larger chip over the back here. There's another chip here, and there's some more circuitry down here. So if we take a look at their schematic, you can see up the top here, this is actually what looks like a real-time clock. I haven't actually looked up the part number, but it almost certainly is. We can see there's a battery, there's a crystal, and it looks like it's communicating over the I2C interface with SCL and SDA connections. There's also a square wave output on there as well. So a couple of pull-up resistors there for the I2C, but we're not really interested in any of that because we're just going to focus on the SD card, so we can ignore all that for now. And if we look down here at their connections for the SD card, see they're labelled as SD and MMC. So if we look at the pins here, they've got pins numbered 1 to 9. They're not running in sequence, but they are all there. We've got pin 1, 2, 3, 4, 5, 6, 7 and 8 and 9. So they're all there. If we just run down them in the order that they've got them. So pin 7, that's master in, slave out. So it's the data out of the SD card. And then over here we've got master out, slave in, and that is going through that circuit to the data in. Now this here is a voltage level converter. I had a look at the part number down the bottom here, 4050, and found that this is a voltage level converter. So that's all they're doing. They're dropping the voltage down from the 5 volts logic from the Arduino down to 3.3 volt logic levels that the SD card needs. So the SD card is a 3.3 volt logic level chip, hence why it's connected to a 3.3 volt power supply. So the data in does need to be level shifted, but data out doesn't, because the 3.3 volts is high enough for the Arduino to recognize as a high level signal, and it's not going to cause any damage because it's lower, but obviously coming in at 5 volts we do need to drop it down because we don't want to damage the SD card by applying 5 volts to it. So that's why we're level shifting on the way in but not on the way out. And then the next thing is we've got the clock, serial clock, and that is an incoming, so again we need to level shift it down. Now, I originally thought this was a pull-up resistor, but it's not. It's actually just a current limiting resistor connected to an LED here. So whenever the clock line is high, the LED will be turned on. When it's low, the LED will not be turned on. But I'm not going to include that. I'm not quite sure why they've included it, but we can leave that out. We don't need that. The next connection is chip select. And again, it's an input coming in. It's connected to this jumper here, which will probably be connected to one of the Arduino pins at 5 volts, so we will need to level shift it. And this time we do have a pull-up resistor, a 10k pull-up resistor. Now this confused me here. They've got this connected to something called VDDIO, and it took me a little while to figure out what that is. Still don't think I know 100% what it is, but I found it up here on the diagram. There's a couple of references to it here, and also again one down here, and it looks like it's some kind of circuit there that gives you the choice of either connecting it to the 3.3 volts or the 5 volt. That looks like a solder pad that you can probably short out. There's some more solder pads over here, and the symbol looks similar to those. So I think it's there just to give you the choice of the 5 volt level with the high voltage level, whether that is actually a higher voltage or whether it is just the normal 3.3 volts. But again, we don't need that. I'm going to ignore that. We won't have that in our design. We would just need to pull up to the 5 volt level. And then we see we've got pins 8 and 9 with no connection. And then pin 4 is VDD, that's the 3.3 volt power supply. And then we've got VSS1 and VSS2, which are pins 3 and 6. If you remember, the SD card had 2 ground. The standard SD card had 2 ground pins, 3 and 6, both connected to ground. And then finally they've got this GP, which I think probably stands for ground potential. I'm just guessing. But that's probably the casing on the socket itself. But there's a few more pins up here. They're not numbered, and they're not actually part of the SD card itself. I believe these are just pins on the actual socket. We've got one there, GP3, which again I think is ground potential, and it's connected to ground. It's labelled common SW, common switch maybe. And they seem to go up to just to this breakout header here, so they're not actually connected to anything. They're just broken out if we do want to use them. And I'll probably will be using the card detect, but probably won't be using the write protect. So it looks pretty straightforward. We just need to bear in mind about whether we're using a full-size card or a micro card. So let's take a look in EasyEDA at the circuit diagram that I came up with. So the first thing I had to decide was you need to be really careful when you're designing circuit boards that you do actually very carefully look at every single component and make sure the connections are 100% correct and you've got all the physical footprint sizes correct. So I had to make a choice on what actual socket am I going to use for my SD card. So this is one I actually found in the EasyEDA library. It's MR01A-01211. So I've looked at the LCSC website. I plugged in that part number. And one part found. This is what it's come up with. So I took a look at the data sheet. And it's really nice. You do actually get a CAD drawing of all the physical dimensions. So that'll be really handy to check against the part that I eventually end up buying when I make sure that the physical size is the same. And the pin positions and things are the same. So I took a look on eBay And this is the actual part that I ended up buying. And they look like they're the same thing. And they do also have a diagram, a CAD drawing showing us the sizes. And it looks like this is 14.7 millimeters wide by 13.8 millimeters on the shorter edge, on the left-hand edge on that drawing, and 14.5 millimeters on the longer edge. So it looks the same. So if we check against this CAD drawing again from LCSC, I'm looking for that 14.7. There it is, look, 14.7 millimeters wide, so that matches. Yep, and looks like their drawing's the other way around. So they've got the 14.5 on the longer edge and 13.8 on the shorter edge. So it is the same. I think this is just viewed from the other side or something that's been flipped over. But it's also got these two things here. I think they're lugs actually. And they're not quite centre. There's the centre line, and they're slightly offset. And again, if we look at the image on eBay, I think their drawing shows the same somewhere. Yeah, there we go. There's the two holes, and again they look off centre. Again, everything seems to be flipped over, but I'm pretty sure that's just viewed from the other side or something. So these look good. These look like they are the correct part. Part numbers might not be exactly the same, but they look like they're compatible. So the other part I need to look at is the voltage level converter, the 4050. And the part I'm using from the EasyEDA library is called a HC4050 M96. So again, I've looked up the data sheet on LCSC. We take a look at the description here. It says convert high-level logic to low-level logic. And interestingly, it says while operating off the low-level logic supply. Now that interested me because I thought that these things sometimes have two supply voltages at the two levels that they're working at. But this seems to just work from the low-level logic supply. And my understanding is the supply that you give it becomes the low level, and then the high level is allowed to be higher than that, and it will bring it down to this level. Now the part I've purchased is actually called a 4050D. That's what's labelled on the actual chip, and I couldn't actually find any reference to that, so I am a little bit uncertain about that. Yeah, so this is the actual part that I've ordered, and it is labelled there a 4050D. Yeah, and it's also described as a SOP16. So I think SOP16 is the same as SOIC, but we'll find out when it arrives. So let's very quickly run through this schematic diagram, and then we'll get on to taking a look at the PCB. So this is basically the Adafruit circuit with just some changes to pins 1, 2 and 3 to make it suitable for a micro SD card. I've added a couple of minor additions down here. So if we tackle these in the order of these pins, there's no connect on pin 1. Pin 2 is the chip select. I've got a 10k pull-up resistor there pulled up to the 5V line. This is 5V logic level, so we need to level shift it down, and then it goes through to pin 2. The next connection is MOSI, master out slave in. It's an input, it's 5V logic level, so again we level shift it down and that comes in and connects to pin 3. Pin 4 is the 3.3V power supply for the SD card. Then we've got the clock, serial clock, again 5V logic level, so we level shift it down, comes through here and connects to pin 5, the clock. Pin 6 is VSS, that's a ground, so we just connect that down to ground. Pin 7 is master in, slave out, so that's an output, so we don't level shift that, so we just break that out straight there. Pin 8 has a no connect. Now pin 9, this isn't officially pin 9 on an SD card, it's just pin 9 on my particular symbol here. Pin 9 on this symbol is the card detect. And then the last 4 connections are all ground. They're the little tabs on the casing of the card holder, so all connected to ground. Then we just have the 3.3V power supply coming into pin 1 VCC on the 4050. I'm also going to include a 100 nanofarad capacitor. I'm going to position this as close as I can to pin 1. That'll just be a bypass capacitor, just to make sure that this chip gets a nice clean power supply. And then finally we've just got the ground on pin 8. I've also included a power LED. Now I've decided to power it from the 3.3V rail. I could have connected it to the 5V rail, but I figured that if I know the 3.3V is up, then we know that everything is up. I am not sure about what value I'll use for the current limiting resistor. I put 1K on the diagram, but I'll play around with that. I've ordered a few different values. I'm also not sure what color LED I'll use. Again, we'll play around and experiment with that. So the only other thing is the breakout header. I've got an 8-pin breakout header. I'm just breaking out the 5V, 3.3V, the MISO, the MOSI, serial clock, chip select, card detect and ground. So that's the circuit diagram. Let's have a look at the PCB design that I came up with. So the purple line is the PCB outline. So that's the overall size of the board. It's 30mm by 22mm. I've put fixing holes in the 4 corners. This is the SD card holder. They're the 4 tabs, which I said are probably the ground connections. This is the 4050 voltage level shifter IC. Then I've got the power LED here. There's the current limiting resistor for the power LED, so I positioned those close to each other. This is the 10k pull-up resistor. It's connected to chip select. It's not too far away from chip select. Didn't want to position it here because I wanted to leave this area free for these labels, so I pushed it over to the side. And finally, this is the 100 nanofarad capacitor that I've tried to position as close as I can to pin 1. I didn't want to get too close to this fixing hole because I didn't want any screws to be touching the connection. It's not too far away, it's literally just a couple of millimeters, a few millimeters. Yeah, and then there's just the breakout header across the top. So very quickly I'll look at the routing. I'm not going to go over all of it. Let's turn some of these off, clean things up a bit. So that's the top layer routing. I've given it a ground plane. It flooded most of the areas. There's just a little bit here that it didn't get into. I'm reasonably happy with that. I do have to say I found the routing a little bit more tricky with surface mount components. I normally do through hole. So this is a bit of new territory for me to do surface mount. I found it difficult because nearly all of the connections have to be done on the top layer. So we have to use a lot of vias to break down to the bottom layer to actually get the routing through to where we need it. Very quick look at the bottom layer. Not really much to say about that. There isn't too many connections there. Only thing I wasn't totally happy with is the ground plane didn't flood down here. I found it a little tricky to push this up any higher because we've got this fixing hole here, but also on the top layer, this sphere couldn't really be any closer to this capacitor here. So I figured it's just not a big enough problem to worry about, so I left it. I probably could have done something with it. So that's the PCB layout. Then we get a 2D rendering. I think that's going to look okay. Looks okay to me. And then we also get a nice 3D rendering. I was lucky that all the components actually had 3D models, so the whole thing is rendered out exactly as it's going to be. So I'm quite pleased with that. The only thing really left to decide is what colour do I make the circuit board. I think blue is my favourite colour, but I wanted to do something a little different. It gets boring, keep doing the blue all the time. So I looked at green. I think green's okay. Nothing wrong with that. I also like red. I do quite like the red colour. I'm not very keen on the white. I really don't like the white. I don't like the black silk screen. It's an off-colour white. I just don't like it. Don't know why. The yellow isn't really a true representation of the yellow. I find it comes out more like orange. But yeah, that's probably my least favourite colour, with the exception of white. Black does look okay. It looks very professional when you do black circuit boards. It's not quite as deep black as this. It's more like sort of a very dark grey. But it can look a little boring. But it's okay. I do like the black. But I thought what I'd do, take a bit of a risk and go with this new purple. This is JLC PCB's new colour. I've had it out a little while now, but I've never ordered a purple board, so I'm quite excited to get this in purple to see what it's going to look like. So yeah, definitely going to go with purple. I think that is going to look really nice. I mean, it's going to be pretty small. It's a small board, so it doesn't really matter, but I'm quite looking forward to getting that. So I'll get these circuit boards ordered. They'll take about 3 weeks to arrive. A lot of the other components are already on order, but they are coming from China, so they'll take a while to come in as well. Hopefully in about 3 weeks we'll have everything. I'll then make a follow-up video and we'll put the thing together and have a play around with the software, see if we can get it working. So if you liked the video, please give it a thumbs up. And if you haven't done so already, subscribe to the channel. Don't forget to hit that notification bell so you don't miss out on any notifications of new videos as they come out. And thanks for watching, and I'll see you in the next one.